Welcome to OpenGyan. This is the screencast on Linux programming, and this is Lakshmi Narayanan from OpenGyan. Okay, so let's get started. In this screencast, we are going to discuss about process management. The first part of the process management is how to create a process. And in any operating system, in any modern operating system, we need to create a process to get the task done, to accomplish any task. The first thing is to create a process, and then we need to overlay a program into the process and then get it executed. In this screencast, we will be focusing more on how to create a process, and we will discuss other things like how to overlay a program in an existing process address space, and then how to recollect accounting information of a child process that is already exited, and then how to exit gracefully from a process, how to gracefully exit a process. And this screencast will specifically focus on how to create a process. And before getting into the practical aspect of creating a process, it is mandatory that you have a fair idea about what is process, and it is expected that you would have played around with your Linux or Unix system for some time, running certain commands like ls, grep, and then most importantly you would have some hands-on on ps, which helps us to find various processes and its states and process information in a Linux system or a Unix system. First thing is, with respect to Linux or Unix, I don't think we need a specific textbook to learn concepts, and all the information that is needed is readily available in manual page, which can be accessed, the manual page can be accessed using the command man. If you want to read the manual page of let's say like ls, you need to do man ls, so that it gives you the various options or in detail about what does ls do. And with respect to this portion of screencast, which we are going to see about fork, let's quickly read through the manual page, man fork. And by the way, fork is a system call. People call it a system call, and it is also a library call that is available in glibc or a standard C library. And if you are fairly exposed to writing C programs, you would have come across header files, and one such header file is unistd.h, and this fork is defined in this header file. The library called fork is defined in the library file, which is unistd.h, and it is mandatory that you include this header file before you try to create a process. Depending upon the compiler, either it will throw you a warning if you don't include it, or it will throw you an error. And if you closely look at this signature of fork, or the prototype of fork, fork is a function name, and the one that is highlighted, fork is a function name, and it doesn't take any argument. You don't need to pass any argument to fork. And then the fork returns PID underscore T. It returns a value of type PID underscore T. And if you look at it, you will not find this return type anywhere in standard C tutorial or standard C programming book, because this PID underscore T is defined in unistd.h, which depending upon the platform, it may be a short int or an int or a long. So it is safe to assume that PID underscore T is of integer type. It can be anything. It can be short, it can be int, or it can be long. So what happens when you call fork? When you call fork, you duplicate the calling process. So one analogy is thinking fork as a photocopying machine or a Xerox machine. So you have in Xerox machine, you keep the original document on the scanning tray, and you press the go, and you supply the white sheet. Whatever is there on the original document, it gets copied onto the white sheet that you provided. So fork is similar to that of a photocopying machine. So everything included, I mean everything is duplicated, right from environment variables, code segment, data segment, heap and stack, everything is copied as another process. So if you have, before calling of fork, if you have 100 processes running in the system, after successful invocation of fork, you will have 101 processes, and at least there will be 2 processes that are identical. And when I say identical, the content will be identical, but there are certain differences between these 2 processes, like process ID and parent-child relationship. All those things will vary because the process that gets created is called child process, and its parent will be the process that invoked the fork. So after fork is successful, we will have 2 processes. One process will be a parent process, and another process will be a child process. So what happens if fork is successful, and what happens when fork is not successful? These are 2 cases, right? So when fork is not successful, eventually there won't be any process that is created. So the fork doesn't create a child process. So that is an error condition. Either it could be due to lack of permission, or it could be lack of probably like we would have reached the maximum number of process that can be created in the system. So we have reached the threshold, and it is not possible for the operating system to allocate memory or to allocate process identifier for anything for that matters. Operating system doesn't allow us to create any process. So that is the failure scenario, but most likely operating system will allow us to create a process, which means that we have enough resources in hand so that we can go ahead and create a child process. So if the fork is successful, there will be 2 processes that will look alike. One is the parent process, another is the child process. So if in a parent process, if you have you will have code segment, data segment, stack and heap. These will be replicated to another process. So which means that you will call fork once, but it returns twice. Once in the parent process and another time in the child process. So in the case of in both the cases, the return value will differ depending upon whether it is a parent process or a child process. In the case of a parent process, when fork returns, it returns the process ID of the child, and there is a reason why Linux or Unix returns the process ID of the child. The reason is that the process that created the child process will be willing to collect information about the child process. Okay, in the case of parent process, the operating system returns the process ID of the child, and in the case of child process, when fork returns, it returns the value of 0, which signifies that this is the new process and it has been created successfully. Okay, so there are 3 possible return values. One is -1 when fork is failed, and we were not able to create a child process, and when fork is successful. Here there are 2 possible values. One is a non-zero value, which is return value, which is the process ID of the child. This happens in the process parent process, and in the case of child, the return value of 0 is returned back to the caller. Okay, so you can go through this man page for more details, and it will give you a fair idea about fork. And let's quickly write some program using fork. So let's create a file of fork example.c, right? And then let's try to open this in editor called gedit, which helps us to see the C code in a nice highlighted fashion. So it has opened. So here we need to include two header files. One is the standard io.h, and then the second header file is unistd.h, where fork is defined. And let's also write a main program, and this is main function. From here the execution starts, right? So then we will have another local variable PID of type PID underscore t. Let's name it as PID, and let's also initialize that to 0, right? So immediately after that, let's try to create a process, and let us also store the return value to the PID. As we discussed before, and from the man page we learnt that there are two scenarios. One is when fork is failed, right? And then we have other scenarios where fork is successful and the process is child, right? And then another scenario is it is a parent process, so which means that it returns positive integer. If it is a child, it returns 0. If fork is failed, value of -1 will be returned. So let's go ahead and print something in each if block. So here it is an error scenario, so let's try to print error while creating a child, right? Good. And let's also print something here. So here it is PID equals 0, which means that it is a child process. This is a child, and here too we will print something which is, this is the parent. And it is always good practice to return an error code. So yes, so let's try to compile this program. This simple program that it explains few things about fork. Yes, it has compiled successfully. Let's try to run this. So here it prints this is parent and this is child. So in this scenario, after the fork is successful and hence it did not print error while creating a child, and after creation of fork, the execution will start from here, right? Because fork is successful, so this part won't be executed, and the execution now starts from here, right? So now there are two processes. One is the parent process, another process is the child process. So in the case of parent process, the control will directly come to here, because the PID value in the parent process will be greater than 0, because the fork will return the process ID of the child. In the case of parent process, the PID will be a non-zero positive integer, and hence the logic or the control comes here and it prints this. This is the parent, right? In the case of, and then the parent process returns and exits. And in the case of child process, the control won't come here because PID will be 0, and if the control comes here, yes, it satisfies the condition of PID equals 0. It prints this is child, and it won't enter further here because the condition is not met, or the condition is met here, so it comes out of this if loop and it returns, right? So this is how a fork process creation or process will work with this particular example. Let's try to do one thing. Let's try to run this child first, and then by introducing a delay. Let's introduce a delay of sleep of, let's say, like 5 seconds, and then try to compile this. fork_example.c. Yes, let's try to run this. So if you look at this example, the parent is going to sleep for 5 seconds, and by the time we expect that the child will resume execution and it will exit, because the logic in the entire logic is pretty straightforward. It is just printing of something. So by the time the parent wakes, right, the child would have exited. It would have printed this is child and it would have exited, and after 5 seconds delay, the parent process prints this statement, this is the parent, and it will also exit, and that is exactly has happened, right? If you look at this output, if you run it again, right, it prints this is a child immediately, and then the parent process, it waits for 5 seconds, and then it's going to print that this is parent. And let's quickly do one more thing. We can introduce a delay, sufficient delay, let's say around 1 minute delay in each process, in each if structure, right? And then try to compile this program while we are compile this program, right? So yes, we have compiled it. Let's try to run this, but this time we will run this program in background, so that we will have shell available for us to take next set of commands, and we can run the PS and then see what is the process ID, right? We'll play with PS with this example. So yes, we have put the process in background, and let's do a PS-L, which is the long listing, right? So here these two lines are very important, right? So if you look at this is the process ID of the parent. So this must be the parent, and its parent is 2545, which is shell, and then we have another a.out, which is the child process. The process ID is 3793, but its parent is 3792, which is this process, right? So you could from this PS output you could have understood the relationship between the parent process and the child process, right? So with this we came to an end of fork, and before wrapping up this session, I would like to give you a set of exercise that you can try with your Linux system in your fine time. So this is I have 3 exercises for you. First thing is, let me read out one by one. Write a program that creates a new processes in a loop. With this example, try to find out what is the maximum number of processes that can be created in your system. Okay. One thing that you need to ensure is that you don't run this program in your college system or a production system which you use as a email server or a web server. So if you have a system in your home, it is always better to try this out in your home system, where you have exclusive access and you can do whatever you want. But if you are using if you are sharing the system that is being used by many people, and you should check with your administrator, or if you should check with your faculty before trying this out. But to be in safer side, don't try this example in a public system. So that's what it says. Ensure that you don't try this out in your college or a production system that is used by many people. It is safe to run this program in your own system, as this may lead to denial of service, because once you reach the threshold of maximum number of processes, your system cannot create any more processes, and that will hog the system. Okay, so the first exercise is to check what is the maximum number of process that can be created in your system. Okay, so let's move on to the second exercise. Second exercise is write a program that creates a child process, print process ID and the parent process ID in both parent as well as the child process. And you should you can run ps output ps command, or you can use get PID, get PPID. These two are two function calls that are again defined in, if I am not wrong, in unistd.h. You can always check out man pages. The functions are get PID, that will return the process ID of the calling process, and the function called get PPID, it will return the parent process ID of the calling process. Right. Let's move on to the third exercise. The third exercise is write a program that creates a child process, and in the child process introduce a sleep of 300 seconds, which means 5 minutes, to make sure that the parent process exits before child process. Check out PS output and check out who is the parent of the child process. Okay, now, and whose original parent that created the child process is dead. So after the parent process is dead, try to run the PS output and see what is the parent process ID. Okay, these are three exercises, and with these three exercises I think you will be able to get a fair idea about source, and then you will be comfortable in understanding how to create a process, and you will also would have understood the nitty-gritties of creating a process. And with this we came to an end of fork system call, and in next screencast we will see a couple of function calls or system calls like wait PID, exit, and followed by exec system calls. And with all these system calls we will cover most of process management, and from then on we will move on to other areas like file IO, inter-process communication, and memory allocation, and things like that. We at OpenGyan hope that this screencast would have benefited you. As always, we welcome your feedback, suggestion. Please do write to us, and you can contact us either through our website, or you can contact us through our email ID, which is www.opengyan.com. Sorry, that is a website, and if you want to contact us through email, our email ID is ping@opengyan.com.